Welcome to another Simply Diagnostics video. Thanks for watching.
Yeah, today we're going to take a brief look into CAN networks, control area networks, communication networks. We're going to try and demystify them a little bit and simplify it down. There's a lot of people that get confused about CAN networks, what they should be looking for, how to test the systems, and common symptoms of a CAN network failure. So with this video we're going to run through and try and sort it out for you, to simplify it and to, you know, debunk some of the myths and give you some pointers and tips for testing it. I hope you enjoy the video. So first of all, we'll show you the setup, how we've got it set up. We've got a 2012 Hyundai i20 donor vehicle. There's nothing wrong with the car. We're just using it for test purposes today. We've got it set up on a battery support unit, GYS flash, 100 amp. That's just to maintain battery voltage. The last time I worked on this car I killed the battery. We've got the engine ECU at the back with the cover already off it, so I can get access to the wires for testing. Common ground for my scope, and basically what we're doing, I've got a DLC breakout box. This end of the cable goes to the DLC in the vehicle, and then I've just got my KTS file. It gives me easy access to all the pins on the DLC without having to scrabble underneath the dashboard. Simple DVOM for taking basic resistance measurements and voltage measurements. We've got the KTS, we've got the 2-channel scope for the KTS hooked up. A lot of people say, well, I haven't got a Pico, all I've got is my scan tool, I haven't got a snap-on scope or anything like that. And I've been asked to do a video on using the KTS scope. So we're going to use the KTS scope for this one today. So we've got my camera, got my big screen set up with the relevant information so we can see it on the big screen. There's a picture of the DLC connector. You can see top left pin 1, bottom right pin 16. The pins we're interested in today are 6 and 14. 6 being the high speed CAN line, 14 being the low speed CAN line. And then we've got the Veris set up if we need it, and we've got the laptop over there for the KTS. But yeah, so that's all we need. All we really need, a basic scope. It doesn't have to be a Pico or anything like that. Basic scope, breakout box, DVOM, battery support, and somewhere to access the network. And that's about it. Right, so looking at the 16-pin connector, obviously this is a drawing of it, courtesy of obdtester.com. Like I say, the pins we're interested in today are pin 6, which is the high side of the CAN network, and 14, which is the low side. The single wire networks, your K line will be on 7 and your L line will be on 15. 16 battery positive, 4 should be chassis ground, 5 should be signal ground. But like I say, the ones we're interested in today, 6 and 14. So the i20 that we're working on today, I can't get a full network diagram for that without going looking for it. But one of the things that you'll see is up here we've got the fuse box. We've got the data link connector. This is showing 2 data link connectors, but we've got the data link connectors, and then the ABS control unit down here. And what you can see is all the CAN wires. You see the CAN low is on the blue, CAN high is on the red wire, and all the CAN wires, so this twisted pair, that twisted pair, that twisted pair, they're all the same colours. So normally all the wires on a CAN network, all the CAN high will be one colour, all the CAN low will be another colour, and it's normally the same right the way through each CAN network. And then we've got a bit of basic information here from all data. On our high-speed CAN network, 2 terminating resistors, 120 ohms each, are integrated into the PCM and BCM. So that's the engine computer and the body module. Since both 120 ohm resistors are connected in parallel, the total resistance is 60 ohms measured at the DLC. If a control unit is disconnected from the network, 120 ohms must be present between pins 6 and 14 on the DLC. So here we've got a wiring diagram of a Vauxhall Astra. You can see we've got the DLC here, pin 6 CAN high, 14 CAN low. You can see all the CAN, the twisted pairs. The high speed CAN is green, the low speed CAN is white. And all we've got with the key off, we've got an actual what we call the physical layer, and it's 2 pairs of wires going to each module, a CAN high and a CAN low, going to each module. Some of them go through other modules and are bridged out, others just go straight to the DLC. So what we're looking for before we do any sort of scoping or measuring or anything like that, the first basic check we need to do is to make sure that the physical layer, as in the route between 6 and 14 right the way through the vehicle, is intact. The physical layer is actually intact, and it's measuring 60 ohms between 6 and 14. If it doesn't, then we're looking for an open circuit, a short to ground, something like that, or module disconnected. So that's the first check that we're going to do. Right, so the first thing we're going to do, we're going to do a check of the physical layer. We're going to use the Pico breakout box and a DVOM. I've got the Pico breakout box plugged into the DLC in the car. Turn my meter on. Can you see that okay? Yeah. So obviously the one there showing open circuit, I've got it on a 200 ohm scale. Put plausibility check, put the leads together just to check that my meter's okay. That's ballpark, that's good enough for what we're doing. And then all I'm going to do now, pin 6 on the box, it corresponds with pin 6 on the DLC, and 14 corresponds with 14 on the DLC. So all I'm going to do, shove my meter leads into there, and that should give us 60 ohms, which it does thereabouts. Can you see that? Let's just zoom in so you can see the meter. So 61.5 ohms. And what I'm going to do now, all I'm going to do is I'm going to unplug my engine ECU, which is over here where my hand is. I'm going to unplug that, and you can watch the meter and see what happens to the meter. Okay, so 60 ohms. Unplug the engine ECU, which is where one of the terminating resistors is located, and it jumps up to 120 ohms. So that tells us that it's incomplete and one of the terminating resistors is out of the picture. Bearing in mind this check is done with the key off, nothing on, the vehicle asleep. So that's one of your first checks. If you're reading 120 ohms between 6 and 14, you've got a break in your physical layer. So what we can also do now is we can short one of those to ground. So if I just get if I get a jump lead now, doesn't have to be anything fancy or posh. All I've got is 2 4mm bananas. And what I'm going to do, I'm going to go to my chassis ground, which is pin 4, and I'm going to short the high speed CAN out. Actually, before I do that, I'll plug the modules back in. I'll plug the engine ECU back in so we can see we've got 60 ohms again. So we've got 60 ohms back in. I've got one wire to my chassis ground, and all I'm going to do is short it to ground. And see how the resistance doesn't change? And then on the high speed, the same thing. The resistance doesn't change. Okay. But what that tells us is we've got 220 ohms resistors in parallel, and our physical network is incomplete. And our physical network is complete. And a short to ground will make absolutely no difference to the resistance in the circuit. Okay. Now, what I can do is I'll turn the key on. You see, the minute I turn the key on, what happens? The network goes open circuit. And this is why we do the test with power off. Turn the key off. And when it goes to sleep, the meter will drop back down. Sometimes it takes a minute or two for the network to go back to sleep. So this is why you perform these tests with the key off and the vehicle asleep. You can't check a physical network with power going through the circuit. And there you go, the network's gone to sleep and we've gone back to 60 ohms. Okay. What we'll do now, we'll have a look at the voltage levels using a multimeter first. So we change our meter now to DC volts, 20 volt scale. Do a plausibility check with our meter first, so to battery ground, chassis ground, and pin 16, which is positive. Okay, so there's our battery voltage, so we know our meter's okay. We'll leave the ground in there, and we'll check pin 6 first, the can high. No voltage on that, and 14, no voltage on that. And we'll turn the key on. So key on the can low, we've got about 2 volts, 2.1 volts, something like that. And on the can high, 2.6 volts. There's about half a volt difference using a multimeter. So they're good checks if all you've got is a multimeter. Good checks just to check your physical layer and to check the rough voltages with the DVOM. Okay. Now let's see if I unplug the engine ECU. No, actually I'm not going to do that, not with the key on. Yeah, I can do. Oh. Right, so with the keys off, just leave it a second or two. So with the key off, you can see the battery voltage drop down straight away. So we're on 1.48 on the can low with the key off, and 2.8 on the can high with the key off. But the network is still alive, it's just not powered up the same. So what we'll do now, we'll unplug the engine ECU and see if that voltage changes. The engine ECU unplugged. Key off, we've got 0 volts. Key on, 2.5 on the can high. And 2.2 on the can low. So just simple tests that you can do with the DVOM if you haven't got a scope. Key back on, physical layer repaired, 2.1 on can low, 2.6 on can high, half a volt difference using a DVOM. And then if we go onto the scope, you can see there using the scope, I've got the red channel on pin 6 can high and the yellow channel pin 14 can low. Right, so looking at the Bosch scope, we've got the both channels are on. Both are on a voltage measurement, which is signified by the U, and both are set to DC. I've got them on a 10 volt scale, just so it makes it smaller on the video. And you can see that with the key on, we've got 2 signals, can high and can low. And basically what all they're doing, they should mirror each other, which they, if I pause it, you can see. So looking at this, with it paused, you can see that the 2 signals mirror each other. There's a little bit of interference, obviously, because we're using a Bluetooth scope, so there's going to be a little bit of interference on there. We've got it at a 200 nanosecond, is that nanosecond or microsecond? Might be microsecond setting. And what we can see is the can high. If I ever get the actually. Right, and what you can see is, if I just pause it, what you can see is that can high is going from about 2.5 volts to 3.5 volts, and can low is going from 1.5 volts to 2.5 volts on the scope. And all they are is they're mirroring each other. So we'll leave that running now, and let's see what happens when I disconnect the engine ECU and we lose one of our terminating resistors. So I'll leave you focused on the screen and I'll just go and unplug the engine ECU. And with our engine ECU, you can see that the voltages have changed a bit. They've gone a bit broader with one of the terminating resistors unplugged. So we're now touching nearly 4 volts, 2.5 volts to nearly 4 volts, and just over 1 volt to about 2.7 volts, something like that. So there's a change in voltage levels. Plug the engine ECU back in. Everything's live, and you can see those voltage levels have dropped back down, and it's a much tidier signal. I'm going to short the can high to ground, and let's see what happens to that signal. I should be able to do it with just a normal wire, but I'm going to use the test light just for safety. So I'm now shorting the CAN high to ground. You can see what's happened there to the signal. Take it out, and signal returns. Now I'll do the same thing with CAN low. I'll short that to ground. You see what happens there. Take it out, and the return. So you can see the CAN system is a fault tolerant system. And what I'm going to do now, I'm going to short it to battery positive, and let's see what happens there. So CAN high to battery positive. That froze because of the trigger. CAN low to battery positive. That froze. So let's just get rid of the trigger. Let's get rid of the trigger and see if we can so I've just put the trigger now on auto level, and we'll do the same again. CAN low to battery voltage. It's gone off the screen. So let's increase the voltage. Right, so with both with the scales dropped down now, I'm going to shorten to battery voltage. So first of all, CAN high to battery voltage. It takes the whole thing up. Take it away. Battery voltage. That's what your CAN low looks like, shorted to 12 volts. It's bringing raising the voltage level to the whole. So you can see if you've got a short to power, that's what's going to happen to your network. And if we go short to ground, that's what's going to happen to your network. And then the other test we can do is if they short to each other. Okay, so I'm just going to stick that in there, and now I'm going to short them to each other. And that's the network shorted to each other. So that's the high shorted to the low. If you had a twisted pair with corrosion in and they're bleeding off into each other, take it away, and we've got a normal CAN signal again. So there we go. There's CAN 101 in a nutshell. There's nothing really exciting about it, nothing tricky about it. It's just a really basic, simple system. Yeah, so there we are. That's basically CAN systems in a nutshell. Power off, 60 ohms between 6 and 14. You can do the measurements with the DVOM on 6 and 14 with the power on. You look at it, about a half a volt difference in the wires, and if you've got one of your terminating resistors out of the picture, it'll measure 120 ohms. Your two signals should mirror each other, nice square patterns that mirror each other, no big dropouts or anything like that. And like I say, they are fault tolerant networks, so they can be shorted to positive, shorted to ground, shorted to each other, and the minute you restore the actual physical layer, it returns. So there's no great science behind this. You're literally, all you're looking for is nice steady square wave patterns, packets of data. 60 ohms with power off for a complete network, 120 if you've got a terminating resistor out, which is normally engine management and instrument, or engine management and body module. That's normally where the terminating resistors are. There's nothing to it. It's very simple. Very simple. So there we go. I hope you enjoyed that brief insight into CAN. We're gonna get looking at it and look at some real world, real life CAN faults, but the basic principles still apply. And if you've got, you know, if you can grasp them, then network faults are not hard. So I hope you enjoyed that. Don't forget to leave a thumbs up if you did, a thumbs down if you didn't, and if you do leave us a thumbs down, don't forget to put a comment in to tell me why you didn't like the video. I can't get better if you don't tell me what I'm doing wrong. Thanks for watching.
And thanks for watching the video. If you liked it, don't forget to leave us a thumbs up, hit that subscribe button. If you didn't like it, give us a thumbs down, put in the comment section below and let's get a conversation started. We've also got ways you can support the channel now if you look in the links below. We've got Patreon, buymeacoffee.com and a direct PayPal link. Thanks for watching and thanks for supporting the channel. You're awesome.